Good afternoon, everyone. My name is Alistair Graham, and welcome to this ILS webinar on a novel high-throughput approach which can accelerate your polyolefins R&D. On the line as well, we have the presenters Anton Notch, the CEO of ILS, and Karl Kabreska, the project leader who led the build and commissioning of the unit we'll focus a lot of this webinar on. So I'll be moderating today's session, and we'll just start with a short introduction to ILS, since I know our name might be familiar to some, but new to others. Anton will then talk about our polyolefins R&D experience and the design considerations for the unit we're looking at. And then Karl will take over and talk about the automation, share some data, draw conclusions about this unit, and then there'll be a Q&A session. To make this an interactive experience, we will use some polls to collect feedback as we go. And please type questions whenever they come to you, and I'll just sort them and group them, and Anton and Karl will respond to them at the end of today. Please keep in mind this webinar is open to anyone. So there could be your customers or your competitors or other people that you know also on the line. And on the ILS side, there are a few tricks of the trade we won't go into detail in, but we'd be happy to discuss in a later one-to-one conversation. You will automatically receive a recording of this webinar at this time tomorrow. So a brief history of ILS. It was started by Anton in 2005 and has grown well to 50 people, where we've done over 220 successful commissions. We offer a customized laboratory platform which can tackle difficult research challenges across many industries. This could be a high-throughput tool working at a smaller scale to evaluate many different catalysts or process conditions, an optimization tool to look at improving the yield or the selectivity of an existing process, or a pilot plant for doing the scale-up stage. But we're not just hardware. We also have scientific software for managing recipes, acquiring data, analyzing products. We can integrate analytics and robotic units into our reactors to make an overall research platform. And we also offer chemical commissioning and contract R&D services. On the screen there, you can see an example of the high-throughput tool, which we will talk about for a lot of today, and also a pilot-scale polystyrene unit, which we won't go into any detail on, but we'd be happy to describe in a later conversation if you'd be interested. We serve clients across many different industries. This includes petrochemical, pharma, catalysis. We also work with leading academics in different research organizations and work in the automotive sector as well. But today, we'll really focus on the world of polymers. And you might hear a couple of names of our companies we've worked with in this field in the past. And I'd like to say a big thank you to the client who actually commissioned this unit. They kindly gave us permission to make this presentation, and all of the information you see has been approved by them, since we take confidentiality very seriously at ILS. So at this point, I'd like to hand over to Anton, who will then lead the focus on the polyolefins area.
Okay, Alistair, thank you for the introduction. And thank you to all of you for attending today. I see a few familiar names here of people who've come in. Hello to all of you. Those who know me well, it's rare that you get to see me in a dress shirt, so enjoy the opportunity. What I hope to get across today in my portion of the presentation is on how the background of this project went, and what we hope to achieve today as a group is to convince you that we've developed a tool here that can help you do up to 18 experiments a day, that can do those 18 experiments a day with one FTE, so with one operator. So potentially perform more experiments a day with fewer people than using more traditional techniques. Potentially improve data quality depending on what you're currently working with. So if you're working manually, you will likely be able to have a significant improvement of data quality going with this fully automated approach. Perhaps a better reproducibility than some of you which might be working at a very small scale, which I'll go into a bit more detail later at. And last but not least, this is really a single tool which is capable of doing gas phase, slurry, bulk, multimodal synthesis. So you can really do multi-phase syntheses in a single recipe in the use unit, which makes it rather unique on the market. Also makes it a valuable investment as you can cover all of these different syntheses types with this single unit. Just a brief note on how ILS works. This unit is just one of many we've built. So we're not here to convince you that this is the only approach or the best unit on the market. It happens to be a custom unit made for a client. We only make customized units. As you see here, many of our units start off with a simple hand drawing and some basic schematics showing concept drawings. This was for a 4 parallel polyolefins unit, which was made for Evonik, a good reference for us. We quickly moved from that kind of a stage to making P&IDs, where we really get into the detail of all of the field components. What kind of flow rates do you need, heat, mass transfer, all of the details that need to be taken into account to make sure the unit is properly designed. I think it's drawn up in 3D CAD. The software gets programmed. Here we take into account all of your infrastructure requirements, ergonomic factors, etc. And at this point, really, we require your approval, and only at that point do we really move on to the final build. So you don't actually get a unit from ILS until you've actually seen virtually what you're going to get and have participated in all of the steps of the design. Typical production times are somewhere between 6 and 12 months, really depending on the complexity of the unit. And I think it's important to point out, ILS designs really non-proprietary technologies using good engineering principles and a lot of experience. So we don't patent almost anything that we make. It's not part of our business model. So we're in the business of making custom units, and we also really place great emphasis on using hardware and software solutions that give our clients full freedom to modify the units, to own the units in the future. So our business model is not around expensive spare parts or tying you into any sort of exclusivity with us. We really prefer to give our clients the freedom to take complete ownership of the units in the future and do this on their own with full freedom and flexibility. So here, just a brief overview of some of our previous polyolefins experience. The first one I'll mention here is was made for Total. So Olivier Méziac is a very good reference for us, and that was a 24 parallel slurries polyethylene unit, also used for POW synthesis studies. We also work with the group of C2P2. I believe a few of them are present here as well. Originally working with Christophe Poisson's group very closely. They have a 20 parallel slurries phase unit. We've worked a lot with Timothy McKenna the last years as well. These are very small scale, high throughput units, but really primary screening units. So these are not the kind of units you do really detailed testing or kinetic testing. They have the nice possibility of being able to be operated without the use of a glove box. If anybody's interested in more detail on that, I'm happy to give that offline. You basically do the reaction in small glass vials, which is very convenient. We then moved on to the project with Evonik. They call this the race box, which is an acronym that I forget what it means, but it was a very good project that we did collaboratively with them together. It's been presented at a couple of conferences now, and this is a 4 parallel unit where each 500 or 1 liter reactors, 500 mils or 1 liter exchangeable reactor is independently controlled, fully integrated with a robot in a purge box. This isn't really a high quality glove box like we have now, and has the monomer purification system fully integrated into the unit. This was built and commissioned for Evonik, I think roughly 6 or 7 years ago, and has been in operation ever since. And last but not least, just to kind of show the breadth of diversity here, we did this stop flow testing unit together with Timothy McKenna's group the last years. This is a really novel approach for looking at gas phase polyolefins kinetics at very short times on stream. So typically targeted things between, say, 15 seconds and 1 or 2 minutes. And it gives the Use are the ability to really look at growth kinetics at very short times on stream, which determine a lot of the subsequent polyolefins properties. Example here, which you see on the left, is just showing, for example, what typical temperature profiles look like at the outlet of the reactor. So the simplest cases can be used as a quick way of looking at catalyst activity. But because you can remove very small amounts of sample out of these reactors after the short time on stream, for example, 15 seconds, you can actually do good offline analysis. Here you see an EDX analysis of the sample shown. There's a reference to the literature citation at the end of the presentation as well for this. As Alistair mentioned, there's going to be a few polls in this presentation. And the first question that we have to ask you is, what do you consider the primary motivator for developing a new R&D tool, should you have one? So, Alistair, go ahead and begin the poll. So hopefully you can all see that now. Basically, the possibilities that we put in the poll are around yield and efficiency, which are primarily OPEX related, operations related. And the other ones are tied more into environmental aspects. So improved recyclability, looking at, say, alternative feedstocks. So with alternative feedstocks, we're talking, for example, about maybe monomers that are coming from recycled polymeric materials already. So people doing polyolefins depolymerization and then chemically recycling those into new polymers. And the last thing is, for example, more environmentally friendly products. So we're really talking here about things like, for example, phthalate-free catalysts, for example. So Alistair, maybe you can show the results. Okay, hopefully all of you can see that here. So the winner is increased yield with 50%. And improved recyclability came in at 30%. The energy efficiency and alternative feedstocks are both at 10%. So basically, OPEX-related issues and recyclability seem to be the primary drivers. And that ties in pretty nicely with what our assumptions are. We're a small company. We don't always have the ability to know exactly what the drivers are that push our clients to order units with us. We see a lot of publications. I've shown two here right now. There's a really nice one which just popped up, I believe, last week. The Schwarz Group recently did a nice publication of the collaboration with SABIC, really looking at chemical recycling of materials. Clariant has done quite a lot of advertising recently showing their new phthalate-free catalysts, which really derive from the changes that REACH has put where dibutyl phthalates are, for example, forbidden because of environmental regions. So we see there's a lot of driving factors for developing new tools from a business point of view. What are the real R&D drivers? I mean, in a nutshell, basically what this graph just shows, or this slide shows, is if you look at the materials variables or the process variables, the polyolefins world has a huge number of parameters which can be tweaked in order to change or optimize processes. So under materials, just looking at catalyst support, depending on surface area, porosity, mechanical strength, what kind of impregnation route did you take for making a catalyst? And obviously, there's a wealth of process variables, everything from what phase you're working into, what concentrations, to what temperatures and pressures you're operating at. This combined with the fact that there's really a limited number of suppliers on the market for these high throughput and medium throughput tools. So there's a number of companies making single, larger scale batch type systems. But aside from ILS, Unchained Labs, formerly Siemens or Freeslate, as well as ChemSpeed, I don't really know of any others. And to my knowledge, none of the other systems on the market can perform the multi-phase operations in a single platform. Hence, the real driver we see for the system in question. I'll touch briefly a bit on the history of how the system was developed and deal a bit with the mechanical background. And then I'll hand it off to Carl, who will go into more depth on the software and then really get into the meat of the results that were obtained on the unit. A bit of background here. ILS has a real strong background in more typical petrochemicals or refining catalyst applications. The world of polyolefins was a new, exciting, and at times painful learning experience for us. The accelerated learning curve here is really very true. We had 1 year time of working on this unit. To give you an idea of what our samples look like roughly a year ago, you see it on the left. We do a sample a day. They looked horrible, sticky, amorphous materials. With the help of our client, as well as Timothy McKenna, who provided a lot of consulting support for us, and Sebastian, his colleague, we've now been able to reach 18 samples a day. And I'm afraid Carl, who you see here, has grown a few gray hairs in the meantime, but the fact is we're at a very different place today. So I would claim today that we have a much better basic understanding of polyolefins chemistry, how to make units that suit them well. We are by no means polyolefins experts here. Okay, next poll question. This is a really important feedback for us. What is the right reactor volume that you need for your polyolefins research? I'd appreciate your feedback on that. Alistair, go ahead and start the poll. We've really seen quite a shift in opinions on this, at least I have personally, over the last 15 years. So I'm very curious where this poll is going to end up. And it's still shifting about, so I will wait. As soon as I see the numbers balance out here, I'll move on. Okay, we've just gotten a wonderful Gaussian curve, it looks like. So Alistair, go ahead and end the poll. Publish it. Okay, so I believe you should all see that right now. So the winner is 1 liters. That's followed then by 3 liters, 500 mils, and 5 milliliters is the smallest scale. I'm going to show you a couple of slides. So in a sense, this poll is music to my ears. What we really choose as sort of the gold standard on the market is really the old CIMIC systems. And my thanks to Luca Rungo from HT Explorer. Many of you probably know, a company founded out of the group of Professor Busico in Naples, for being able to show this this image. Where the PPR-48 from CIMIC, now Unchained Labs, is shown. This kind of approach, the PPR-48, has the advantage of really being small. You can do a lot of experiments in a small footprint, fit all the reactors in a glove box, and operate them with really small amounts of reagents and virtually no waste. The downside is the errors are often a bit larger. It's hard to get references there. One I got here was, and you'll find it at the bottom, there's a wonderful YouTube video that's published of an Unchained Labs webinar from Nick Friedrichs at SABIC. And to quote Nick, they were able to achieve a variation for Ziegler nanohomopolymerizations of plus or minus 10% versus his long bearded laboratory technician who was able to do plus or minus 5% at the time. Luca kindly provided me yesterday a publication showing that his lab can actually do 6% now. So in all fairness, if you have a lab like that, which has 15 years or 10 years of time to invest in a tool, you can really get a lot out of it. But generally, working at small scales is very challenging. It also requires, as you see here, the full polymer workflow. So if you don't have the entire workflow for doing your polymer analysis, it's hard to work with 200 milligrams of a product. Multi-step and gas phase synthesis are difficult to do in this kind of kit, and gas cap composition control is also not possible. Hence, the feedback from our clients that we've been talking to over the years has been really that 500 mils is sort of the lower limit, and that matches quite nicely the poll results here. So I appreciate all of you participating in that. At 500 mils, it's easier to achieve something closer to the 5% variation. We haven't always gotten there, but we've come really close for most types of syntheses. And it also makes it possible to work with more traditional characterization methods. Not everybody has the entire characterization workflow that a company like HT Explorer has. It also requires less implementation of, let's say, a highly proprietary technology that, for example, ChemSpeed might have, giving you just more freedom to tweak the unit as you see fit. Hence, we decided to go with a 500 milliliter reactor for this unit here. To give you an idea of the kind of functionality required per reactor, you'll see you have full control over all monomers dosed, hydrogen, co-monomer. You can manually add salt via salt feed port in the glove box, and automated catalyst and co-catalyst injection are also part of the system. You can also do calorimetric studies by measuring the inlet and outlet temperatures of the cool medium. You see what the reactor looks like here to the right. We also wanted to make a scalable modular approach. Sometimes we have clients who want 1, sometimes you want 6. This scalable approach means we can really upscale or downscale the unit made here very easily. Each module here, you have 2 reactors which fit nicely under a module of a glove box. We worked with inert here. We can also work with M. Brown. Online GCs and cabinets are on the back. That means each module has its own online GC, its own control cabinet. All of the mass flow controllers are mounted behind the reactor, and you have a co-monomer vaporizer as well for vaporizing, say, 1-butene or 1-hexene if you want to do any co-monomer incorporation studies. Last but not least, we developed our own unique slurries handling robot. We decided to go this route because you've got a rather long track length to cover with the 3 modules like this. We work with standard Festo components. This allows us to mix catalysts, co-catalysts, contact them for predefined contact times, inject them under pressure into the reactor, and get excellent reproducibility, and all of that in an inert glove box atmosphere. One advantage of this modular approach is the entire module can be removed, tweaked, changed, tested outside of a glove box, and simply slid in from the one side, and you only have to close the one glove box closure afterwards for any maintenance or repair work. And one of the last things we had to address was where to put the reactor. So as I showed, for example, the Siemens or Unchained Labs approach was to put them in the glove box. Advantage, as I show here, is that obviously it's completely inert. We found that handling of these larger reactors within a glove box is really difficult. Anything larger than 500 mils is probably impossible ergonomically. Hence, we chose to put the reactors outside of the glove box. Gives it much easier accessibility, makes it easier to clean, and allows us to use the glove box space really for the robot and for all of the storage samples, vials that we have. So really using the glove box for what it was actually made for. That's it from my side. I'm more of a hardware guy. I'm going to be handing things off at this point to Carl. He's much younger and more adept at software than I am. He'll also be going into all of the results that he derived with the system. Thanks for listening, and I'll hand this over to Carl at this point.
Thank you, Anton. Welcome from my side as well for this webinar. We will go through, as mentioned, a bit of software, and in the end, the data produced with this unit. First of all, how does ILS approach the automation? As Anton mentioned before, both hardware and software are designed to have full freedom to modify and maintain the unit yourself. So shown here is a basic description of how we work with software. So basically, as a starting point, we have our PLC, so process control system. At ILS, we work with Siemens S7 most of the time, but other options are available. So Allen Bradley, Honeywell, the names you know. Major thing there is that we leave all the safety and alarm functions at the PLC side, so no intervention there from our side there. The user then works with the HMI PC, where for example, for Siemens, it's the WinCC runs, where all the interaction is happening. And on the HMI PC, we have our custom ILS workflow manager, along with an OPC server. So the ILS workflow manager then communicates via OPC protocol with the PLC, and thus does all the data handling over the OPC connection. And the safety and alarms are still on the PLC side, so no problems there that you can overwrite an alarm or go out of the safety specs. We also have the possibility to run have a database connection via the workflow manager, as well as creating experimental reports with the workflow manager. So they can be customized to your needs as you want to. So this is how one side of our HMI looks for this particular unit. As you see, there is a lot of stuff on there, a lot of things that you can tweak, set points, switch on, switch off, all these kind of things a normal user would have to work with. But for this unit, we took the approach to actually implement, it's a bit small to see here, but we zoom in a second, we implemented different operation modes. So as we said before, we can have a batch operation, a slurry operation, gas phase operation. For this example, we go for a gas phase operation. So you see the HMI is now only showing the most important features that you will need for a gas phase reaction. In the top right corner, we have just a basic overview over all the pages that are available to the user. So every single reactor, a module overview page, settings, data exports, trendings, all these kind of things that you want to have in a PLC system. Then in that corner right here, we have automated step sequences, which is a feature that our automation guys implemented to make the ease of use, to maximize the ease of use with the robot, as it is basically preparing the injection chamber for injecting the catalyst, then pressurizing the injection chamber with the second step, and then finally injecting the catalyst into the reactor. On the in the top bottom right corner, we have a dedicated trending window, which is unique to that reactor and that reaction mode. So you can define your trending window as you wish for that type of reaction and that type of reactor, or that number of reactor. Then we have our pressure control there, which is set up with an Quillibar solution. So we have a very good pressure control there. You will see that in the data in a moment. And for the temperature control, we have that solution right here. So we have an evaporator or preheater. So we keep the gases or heat the gases up to reaction temperature. We do have a lid heater, and then we have a primary secondary control for the reactor temperature. So checker temperature and inner temperature to control the reaction temperature in a very good manner. And finally, we have a ratio control to control the gas phase composition, along with a GC control feedback loop. So you see we have all the gases mentioned here. With then you can just write in that column right there, you can write the set points, so the concentrations you want to have in your reaction. And right next to that, you have the GC value there. So 200 is written right here because the GC wasn't switched on during that screenshot. Going a bit more into the gas phase analytics and feedback control that is available with this unit, we are using Siemens process GCs on this unit. They do have a response time of roughly 1 minute, which gives us a good amount of data to use the GC as a feedback device. On the right here, you see a trend from a reaction that we did with a gas phase composition control. So we have the start of the reaction right there, and after a couple of minutes, roughly here, we have a almost linear response to our concentrations. So we actually reach the concentration or achieve the concentrations desired and keep them right there where we want to have them. So another poll. Alistair, would you be so kind to bring up the poll? As we are using a lot of scientific software, it interests us what is missing or problematic in your scientific software. So is it difficult for you to build an experimental plan, difficult or challenging? Does running the experimental plan pose problems for you? Or is integrating the plan with your analytical or process data complicated? So having the data feedback into your recipes, or as the last point, processing and analyzing the data created. So for example, live feedback controls, live trendings, yields, calculations, all these kind of things. So we are quite interested into knowing what's your driver, what do you need from a scientific software. I'll just wait a couple of minutes, a couple of seconds till we reach an equilibrium. It looks quite clear at that moment. Okay, Alistair, please end the poll and publish the results. So as we see, integrating the plan with analytical and process data created is the most important for you. And then as runner-ups on the second place, we have all the other options, which is quite interesting. We will touch back on that in a second. So first of all, I mentioned it before, the Workflow Manager. It is the tool we developed at ILS as a recipe engine and as a scientific software package in general To give you a short overview, I'm showing a recipe that we used on this unit for a PE slurry experiment. Here I showed the most important process variables and divided the whole experiment into logical steps. So we start with a leak test, then go into a baking conditioning, inject our co-catalyst scavenger, then add our solvent, do the reaction preparation, so pressures, temperatures, and then finally we inject our catalyst and wait for our set reaction time. This configuration I show right here is basically, I made that up. You can configure any other solution that comes to your mind or suits your needs best. So it's in completely open architecture. You can set those blocks in a different way. You can leave those blocks away. You can just have your input fields positioned freely over that panel. We do have start-stop functionalities. So we do have a stop button here. We have the pause button and a skip step button. So if you want to pause your recipe, just want to check something, you can do that without any issues. Stopping, no problem at all. And starting, of course, isn't a problem at all. There are different levels of information available. So in the top, we have here a dialog box, which you can see says user, developer, and debug, which is basically showing just different levels of information. So the user sees a step has been executed successfully. The developer wants to see if for example, a loop was executed successfully. And at last, the debug level just shows every single step the workflow manager actually did. So every communication step and all these kind of things. Also, we have the option on the front panel to implement trends, progress indicators, dials, other indications that you want to have on your experiment to have a live feedback that is maybe not shown on the HMI or not possible to show on the HMI. Here I've shown a progress indication via a color change. So basically what I did there is if a step has been successfully executed, the box just turns green to indicate the user that that step has been executed. Now for the nuts and bolts of the whole programming aspect. So we chose a object-oriented approach for our programming here to just maximize the ease of use. So with an object-oriented programming, you also have, of course, drag and drop functionalities. You also have the possibility to prepare standard steps or procedures to minimize your programming time. So for example, here you can see we have a pre-prepared automated leak test that basically pressurizes the reactor, holds that pressure for a certain amount of time that can be freely set, and then looks at the pressure loss after some time and then decides on whether the pressure test or leak test was successful or not and gives a feedback to the user afterwards. So how to add those standardized steps? Basically what you see on the left side here, we have a list of steps or recipes, sub-recipes. And for example, if we were to say, okay, after a leak test, the next step would be conditioning or baking. So what we basically do is click and drag this over into this programming panel. And then we have our baking step right there. With a couple of clicks, you then add your controls here. So how many cycles should be done, how high should the baking temperature should be, how high the pressure, and how long should one cycle be held. So you see, if you have standardized steps, for example, in a PO environment, then you just have to prepare those steps once and then drag and drop them into your recipe and align them as you want to have them. We also have we also prepared standard building blocks for the communication with the unit. So writing set points, reading out process values, switching valves, switching controllers on and off. We have that prepared. That is inside of the whole package as well, along with all the functionalities a programming language offers you. So we are using LabVIEW here. So if you're familiar with LabVIEW, you can do a lot of things with LabVIEW. You can do whole communication setups or analysis, calculations. All these kind of things can be done with that recipe control as well. So this is basically the the other side of the front panel we saw earlier. So we are having all the steps that are needed to make a full recipe or a full experiment. So starting with the leak test, going over all the pressures, so hydrogen and ethylene there, injecting our catalyst, and then at the end, cool down the reactor, release the pressure controlled, and finally give the message that the experiment has been done successfully. So you see, even with such complex recipes as a polyolefin recipe can be, the structure is quite clear, and still you can still look at it and understand what is happening. So we saw in that poll that we have your problem with your scientific software is that you want to have the implementation of your process data created into your recipe. What the workflow manager can offer is, for example, a database input or an Excel input, however you want to realize that, to basically have all your process parameters, for example, pre-programmed in that Excel or database, and then just press play on the recipe, and it will grab that data from the database and use that on that recipe. Other way around, of course, it's also possible to push all the data created while doing the experiment, push that into your database to work with that further on, along with calculations on the way. So selectivity, yield, not for polyolefins, but for other applications are possible without any issues. I hope that answers your need. If not, please type in other questions if they are possible with the workflow manager into the chat. We will address them later. So for the chemical commissioning, we did with this unit. We tested 3 different reaction modes for the client. So we started with a PE slurry, then went for a PE slurry with the GC headspace control, and finally a PP batch reaction. In total, we did 150 experiments roughly, so 50 each. And we have to say, we are proud to say that we we surpassed the expectations of the client in all points. So the yield reproducibility was way better than expected. The catalyst activation and deactivation profiles match their experience in larger scale experiments, so with larger reactors. And the molar weight distribution was, or the expectation for the molar weight distribution was exceeded. Especially with the PE slurry with the GC headspace control, we had excellent results for the polymer properties. For our own testing, we were provided with a Toho catalyst by the group of Tim McKenna. Many thanks for that again. They also supported us with at the start of the whole project with knowledge about polyolefins, how to run recipes, and gave us good feedback on our results there. Unfortunately, we had very limited time to do our testing, as that is a client unit, and we have to ship that at some point, of course, so we can't fill with that too long in our labs. But luckily, we made some experiments and are able to show you some data today. So we started our all our experiments. We start with a leak test and then go into our baking or conditioning. Some of you may wonder why the conditioning is kind of short here. What we found from our experience that a high number of cycles with vacuum and pressure is sufficient to reach good yield results with your experiment, and it saves a lot of time for us as we are going for a high throughput application, and we didn't have that much time for our testing. Then we go for our reaction preparations. So we have our scavenger injection right here. So the purple line you see is the injection chamber pressure. So you see it was pressurized and then immediately injected into the reactor. We then have our solvent addition while heating up, along with pressurizing with ethylene and hydrogen. And then we have our catalyst injection for the start of the reaction. So you can see that we have a slight exotherm at the beginning of the reaction, but afterwards the reaction temperature or reactor temperature is under very good control, along with the pressure, which is basically a straight line. So we don't have any issues with our pressure control there. It's basically excellent. Just zooming in on the reactor temperature here, so you see we have some deviations, or you could say some noise on the temperature right there, but that is basically the resolution of our temperature measurement. We do use a PT100, but unfortunately the used Siemens cards on that unit aren't that accurate, so we went for the 0.1 accuracy there. You see the ethylene uptake curves look like in the literature, you could say, so no surprises there. For the results, here shown are two basic experiments we did on the same day. The relative standard deviation is below 6% for one reactor, so if you're just looking at the results for reactor 1 or 4 or whatever, and the relative standard deviation over 12 reactions, so over all reactions shown right here, is even below 3%, so excellent reproducibility there. What we also found quite interesting, and just wanted to show that we are not the experts on polyolefins. What we learned the hard way is that your catalyst loses a lot of activity over the course of one day, for example. So we see those experiments were from the 11th of May and the 12th of May. So after one day, you get a significant drop of activity due to aged catalyst. We learned that quite fast, and obviously then used fresh catalyst from that point forward. Now going for a polypropylene batch experiment. So we are starting with a leak test again, then going for our accelerated conditioning. Then we add our co-catalyst right here, add our hydrogen, and then fill with propylene while heating up. And then as soon as the temperature is stable, we inject our catalyst. We here have a very, very slight exotherm. There we found that propylene or liquid propylene has a very high heat capacity and thus doesn't respond that extreme, you could say, to the catalyst injection in terms of the temperature. You see over the time we have a very, very good temperature control. Again, as it is a batch experiment, we don't have any control over the pressure. It basically depends on the reaction. In the end, we also added a propylene flash right here to make sure that we don't have any dissolved propylene inside of our polymer anymore, for safety reasons, obviously. So if you're if the user's opening the reactor and it doesn't has to breathe in any propylene anymore, along with nitrogen flushing, of course. So all the data shown here was made with the workflow manager. So all the recipes were programmed in the workflow manager and were executed with the workflow manager. For the results for the polypropylene slurry, the relative standard deviation within one reactor is again below 6%, and here the standard deviation over 12 reactions is below 9%. So a bit not that good as with the polyethylene, but there's still some room for improvement there, of course, as we didn't have that much time, unfortunately. Now going for the really interesting part, a multi-phase reaction, which is the one of the key points for this unit. So starting with the leak test and accelerated conditioning again, then going for the pre-polymerization, which is a slurry experiment with ethylene and nitrogen. We use as a solvent, we use propane here. So you see the propane filling here where it goes liquid. And then our catalyst injection along with the very good temperature control and pressure control. And then we change the reaction conditions to a gas phase reaction. So raising the temperature and lowering the pressure there. So zoomed in a bit, you see we don't have a real exotherm at this point. This is probably due to using very old catalysts, as this was like a couple of days ago only. We didn't have that much time anymore. So we had to do a quick test there, and unfortunately the reaction didn't went that well. We had another reaction beforehand that you see in this picture right here, which we actually overshot a bit with the catalyst amount and filled the whole reactor with polyethylene. But it's I'm happy to say that this 500 ml reactor actually fits 136 grams of polyethylene produced in a gas phase. So quite good, quite a volume there still. Okay, so wrapping it up, what can you achieve with this tool? Why is this kind of a tool or could be a good addition to your laboratory? you can do up to 18 experiments per day with one full-time employee. This is due to the fact that we do have our recipe engine, which takes control over the 6 reactors without any manual intervention needed. And thus you have a lot of time for the full-time employee to clean other reactors, to prepare other reactions, to prepare the samples for analysis. All these kind of things can be done while other reactions are running. You receive better reproducibility than with manual operation, as you don't have the margin for human error. So the pressures are always on point, the temperatures are always on point, the catalyst injection is always made when the temperatures are really stable. You get also better reproducibility than with a very small scale operation. As we saw, the yield can be, or the relative standard deviation on the yield can be very small. You have improved scalability to a full-scale process. As you are producing more and more polymer, the reactors get bigger and bigger, so the thermal effects come more into play. You also have sufficient material for full materials characterization. As I said before, one reactor can fit up to, let's say, 100 grams of polymer without plugging everything. And you maximize your investment with a single tool for gas phase slurry bulk reactions and any combination possible with that, so multimodal reactions. So a whole Lyondell-Basel Borstar process. All these kind of things can be done in one single reactor and one run. So this kind of project wouldn't be possible without a very good team. Here shown are the guys that helped realizing this project and get it to the point where it is right now. Many, many thanks to them. Without them, it wouldn't be possible at all. Thank you guys for your attention. I will now give the word to Alistair, which will go through the questions.
Okay, thank you very much, Carl, and also to Anton for that presentation. So we have some time for Q&A now. I think before we start, as we were going, I realized I might have left a typo on one of the slides. I think the catalyst was actually, it was similar to Toho, but not actually a Toho catalyst. So sorry, that was an error on my editing part. So we have a few questions that came in during the webinar, but we have a few more minutes, so you're welcome to type anything in the chat box if you would like, if the question has just come to you. The first question I saw was from Christian. Carl, you showed some reaction profiles when you presented, but could you just say how fast is the transition from one process stage to another? And you're welcome to put your webcam on as Scott.
Yeah, so what we have here is the unit basically uses a aluminum jacket with integrated cooling channels and heating cartridges. So the transition isn't that fast. What you saw there is roughly about 5 to 7 minutes. So from pre-polymerization to gas phase polymerization. So the slow part there is really the temperature. But if you plan on running those kind of experiments in your unit all the time, or you focus on these kind of experiments, it's possible to actually change up the heating and cooling concept a bit to make it way more dynamic to fit those needed dynamic changes on temperature and pressure. I hope that answers your question. If not, please feel free to type in again.
Okay, thank you, Carl. And I think you might also be able to help with a question from Melanie. She asked, are you using the kind of experiments in order to optimize the reaction parameters?
No, we are not using the design of experiments in our labs, as we are a custom unit manufacturer. So we are not doing very much of contract testing, for example. But it is possible to do an integration in your design of experiments system in your lab. So we can talk about that and but find a way to integrate your system into the workflow manager or into the automation of that whole unit.
Yeah, most standard DOE packages can allow an export of a CSV file or something similar, which we can easily import into the workflow manager. So that's definitely doable.
Thank you, guys. And Anton, maybe you could help with Gurmeet's question. Is solid catalyst injection possible?
We are dosing solid catalyst, Gurmeet, but we're dosing them in slurry. So I'm kind of guessing your question was, can we dose just solid catalyst? No, at the moment we can't. So we don't have the ability to dose. Typically, I think roughly 2 milligrams of catalyst was used for a run here. We do not have the ability with this setup to dose just a solid catalyst. There might be a possibility of doing it manually if it was mixed in with a salt bed, but I doubt anybody would do that. So again, we're doing it purely in a slurries fashion in this unit.
Okay, thanks, Anton. And Carl, I'll put this question to you, but Anton, you can feel free to comment afterwards as well. Christian asked if you changed the conditioning procedure when you shifted from PE to PP and vice versa.
You saw that probably on the trending. We did a slight change, but it's actually not due to the fact that we changed from PE to PP, but more that we saw that if we put more cycles in there, along with a slightly shorter holding time from the pressures, we actually get a better yield while keeping the overall time of the reaction basically the same.
Okay. Thank you. And Eve asked what the variability was across the runs and for the copolymers.
We didn't produce any copolymers, so they were all homopolymers, so only PE and pure PP. And I don't know the exact variancy on the reactions. I would need to look that up. But if you're interested, I can send you the data on that, and we can talk about that if you want to.
But what sort of standard deviations did you quote, Carl?
The relative standard deviation for the PE experiment was over the 12 reactions we had was below 3%, and for the PP experiments it was below 9%. So a bit higher, but as said before, it can be still improved.
Thanks. And Carl, Luca asked what was the failure percentage in the catalyst injection at high pressure?
We actually don't have any failures anymore. We had that at the beginning of the while commissioning the unit, of course. We learned along the way, as Anton mentioned, we had a very steep learning curve. We don't have any, or we don't see any difference really between a PE experiment where we inject the catalyst at 10 to 15 bars with 5 bars reaction pressure, or between a PP batch experiment where we inject our catalyst at 55 bars, for example. So both pressures or those pressure ranges or over all the pressure ranges, it works perfect, basically.
Thank you. And Gurmeet asked, Carl, what was the reason for catalyst deactivation overnight, and that under inert conditions, normally deactivation isn't observed?
Yes, this is basically true, but probably, I don't know it from the top of my head, but maybe the glovebox atmosphere during that time wasn't the best anymore. So it wasn't at, let's say, 0.1 ppm of oxygen, but maybe more in the range of 5 to 10, which is kind of acceptable, but still poses obviously a problem for the catalyst, it seems like.
Gurmeet, maybe I can jump in there as well. Our infrastructure in the lab is very primitive for this kind of chemistry. This was really part of the learning curve. So it started with how do we dry our solvent? Yeah, so we went old school and distilled it over sodium. Thank you to the participants who helped us with that. And that reflected itself a bit in the glove box atmosphere as well. So you could literally see if a sample was left open for a long time, Carl, you've seen that, the color would change over time, and you do see it turn white eventually. So the ILS units that we typically make are not really these kinds of air and moisture sensitive units. So with a bit of MacGyver-like improvisational skills, the guys managed to get things up to the purity levels required for these tests, but it is by no means optimal.
Thanks, Anton. Carl, we've got a question from Yasmin. It's nice to see you, Yasmin. What is the reaction duration to produce 100 grams of polymer?
Yeah, so for that particular experiment, as I said, we overshot a bit with the catalyst amount. So we had 20 grams of polymer probably in the pre-poly phase, as we only dosed 20 grams of ethylene in there. And then afterwards transitioned to a 60-minute gas phase reaction, where the rest of the polymer was produced. So with this high amount of catalyst, we achieved 100 grams of polymer in roughly an hour, you could say.
And Anton, maybe you could help with Christian's question. He said it's a very sophisticated piece of equipment and impressive, but how could you run 18 experiments per day?
Basically using the workflow manager. This whole unit is operated exclusively from the workflow manager. So from just a purely software point of view, it's a few clicks and then it started. In terms of cleaning reactions, the reactors, it would make sense if you were to do this on a regular basis to have a second set of reactors. The stirrers and the reactors themselves are very easily removed. And except for instances like the last one where we overfilled the reactor, it's generally very easy to clean them after reaction. So typically you'd have an oven baking out your glassware in an oven, and you'd have a second set of reactors and stirrers for exchanging. And with that, it should definitely be possible to do 18 samples a day. I hope that answers your question.
Thank you. Fabio asked Anton, do we offer technical support in the Americas?
We don't, not directly. So we're located solely here in Europe. I think what's important to note at that point, if you look at the unit we showed, you'll be getting a video of this offline as well, by the way, one of you asked that. Everything in this unit is commercially available, and we really try and focus around designing our units using our clients' in-house standards. So for example, mass flow controller types, et cetera, et cetera. So we really encourage our clients to be able to do as much maintenance work, for example, themselves as possible. I'm not going to claim everything can be done by yourself, but the majority of it can. And I think that's a big difference between us and say ChemSpeed or Symix, or say Unchained Labs. They make fantastic products, don't get me wrong, but you're very much tied into them. In our case, if a mass flow controller breaks, if a robotic component breaks, we work almost exclusively with commercially available components.
Thank you. And Anton, the last question is from Yasmin again. Is it possible to couple the setup with the CEM evaporator?
Yasmin, I take offense at this question. You don't like our vaporizer. So yes, you could. It would be no problem. We work a lot with the Broncore SEMs, and it's pretty well known from the literature as well that it's a good way to do co-monomer vaporization in a pulsation-free way, for example. For a variety of reasons, we did our own. It's a bit more compact, but integrating a SEM would be no problem. It's a product we're familiar with, and it's a very high-quality product.
And Anton, we've just had an additional question from Christoph. Can you continuously feed the reactor with a liquid co-monomer?
At the moment, yes, you can, but it's actually made to be vaporized before entering reactor. But it is there. There's actually 2 Coriolis mass flow meters as part of the overall battery on mass flow controllers, which are made to cover a very broad flow range of co-monomers. That's the reason there's 2. So we typically double up our hydrogen flow meters for metallocene and Ziegler-Natta systems where you need very different hydrogen partial pressures. And in that case, we had 2 different Coriolis flow meters for wide variation of co-monomer as well. So yes. Carl?
Yeah, just to add on that, we were able to dose the co-monomer and propylene liquid with another set of Coriolis mass flow meters or mass flow controllers. And we do have the possibility even to add a very low amount of special co-monomer that is in the glove box or located in the glove box. So we do have a 1 liter or 500 milliliter sway shock bomb there, which can be pressurized with 55 bars of nitrogen to ensure the pressure there, and then can be fed through those Coriolis mass flow meters. So very exotic co-monomers are possible as well without having the need of having a whole bottle, for example, of that available in your lab.
Yeah, what wasn't shown here, which might interest some of you, there's actually a small separate module, which is actually the liquid gas purification and pressurization module. So we have some LEVA type membrane pumps, which pump the propylene, for example, or butene in recycle over the purification columns, generate the necessary pressure head, and then send that pressurized liquid gas over to the main module, which we focused on today. But we didn't show that one here.
Okay, thank you very much, Anton and Carl, for answering the questions. I can see we've had a few additional questions come in, but the clock is going a little bit just now. So I think for those, we might answer those by email to the people who asked them. And in the interest of time, I think we'll kind of start to wrap up today's webinar. Thank you so much for attending. We're welcome to talk to you afterwards about anything which interested you, because we're really proud of this technology and we're really happy to describe it in more detail to see how it could help you. And the last thing before we actually close things down is I'm going to share a link on the screen just to gather your feedback on both what you saw today, but also polyolefin research in general. It only takes 3 or 4 minutes to fill out the survey. You can see a link to. I really value your comments. So last of all, on behalf of Anton and Carl, thank you so much for attending, and enjoy the rest of your day. We look forward to talking to you again in the future.
And a welcome thank you from me again, especially having Tim and Yashmin there as well, and Christoph, all of you. It's been a pleasure working with you, and you've all been a great help over time and educating us about the niceties of polyolefins. Again, you all get a link for this video. I see the question has popped up a couple times, so no worries about that. You'll get that after completion of the presentation. Thanks for participating.